Welcome back for another deep dive. We got an interesting request from a listener to dive into computability and complexity.
Oh,
And I
nice.
got to say, it's a fascinating area where math and philosophy really collide.
Yeah.
Our listener sent in this excerpt from the Stanford Encyclopedia of Philosophy on the topic. And um, it
Good.
got me thinking, about what problems can even be solved by computers, like in theory, and then also in practice, right?
For sure. It's amazing to think that even before we had modern computers,
Right. Yeah.
mathematicians in the 1930s were already grappling with these
Like
ideas.
they were peeking into the future, right?
Okay.
So for our listener who's coming at this more from a philosophical angle,
Yeah.
where should we even start unpacking all
Well,
this?
a good place to begin is with Hilbert's dream.
Okay.
So David Hilbert, he was this brilliant mathematician in the early 20th century, and he had this incredibly ambitious goal
Yeah.
of creating what he called a decision procedure for all of mathematics. So imagine an algorithm, a set of rules, that could tell you with absolute certainty whether any mathematical statement was true or false.
A universal truth checker for math.
Exactly. That was Hilbert's dream.
That's ambitious.
Yeah.
So what was his approach?
Well, he was really focused on something called the Entscheidungsproblem.
Okay.
It's a German word.
It sounds intimidating.
It sounds very intimidating, but really what it's about is determining if statements in first-order logic are valid.
First order logic.
Yeah, it's like this foundational language in mathematics.
Right.
And how we express ideas in a very precise and formal way.
So if I'm understanding you correctly, Hilbert wanted this system to determine if a logical statement, holds water, basically.
Yeah, it's
Sort of like a judge in a mathematical courtroom.
Yeah, that's a great way to put it. And for a while, it seemed like Hilbert's dream might actually be achievable.
Really?
Yeah. So we have Gödel's completeness theorem, which came along and showed there's a way to list out systematically all the provable statements in first-order logic.
So we can make a list of everything we can prove. That's
They can't.
that's impressive.
It is impressive, but
But I sense a but coming.
there is a but, and our philosopher listener will especially appreciate this.
Okay?
So the thing is, Gödel's theorem doesn't guarantee that we can list out all the true statements.
Uh-oh.
There might be mathematical truths that we simply cannot prove within our systems of logic.
Wait, are you saying there might be truths out there that will always be beyond our reach? Like forever?
That's a possibility, and it raises some really deep questions about the nature of mathematical truth.
Right.
And the limitations of formal systems,
Yeah.
and whether there are things that are inherently unprovable.
It's like it challenges our whole understanding of what's knowable.
Exactly.
Okay, so Hilbert's dream kind of hits this Gödelian roadblock.
Right.
But the quest to understand what's computable, that didn't stop there, did it?
No, it didn't. This is where those fascinating Turing machines enter the picture.
Ah, yes, Turing machines. They've always seemed a bit mysterious to me.
Yeah.
Our listener might appreciate a simple explanation like, what exactly are they?
Okay, so imagine a very basic machine with, let's say, 3 main components.
Okay,
So first, you have a set of internal states.
okay.
These are like different modes that the machine can be in.
Okay.
Then there's this infinitely long tape divided into cells, and each cell can hold a symbol.
So it's like a kind of a long strip of paper.
Yeah, exactly.
Okay.
And the tape acts as the machine's memory, right?
Okay.
Finally, there's a head that moves along this tape, reading and writing symbols based on a set of rules.
So it's like a little robot moving back and forth
Yeah.
on this endless ticker tape
Yeah.
and writing down symbols as it goes.
Exactly.
It's on some instructions.
Yeah.
Wow. Okay.
Now, here's the kicker. These deceptively simple Turing machines are believed to be capable of carrying out any computation that's possible, in principle.
Wait, so anything like a supercomputer can do, the Turing machine could also theoretically do, given enough time and tape.
That's the idea.
That's pretty incredible.
And this has some pretty mind-blowing philosophical implications as well.
Like what?
Well, for instance, if we think about, thought and intelligence, could our minds be a kind of Turing machine?
Oh, wow.
Could consciousness itself be a form of computation?
Those are some big questions.
Big questions.
Okay, so Turing machines are incredibly powerful.
Yeah.
But I have a feeling there's a catch.
There is a catch.
There's got to be a limit somewhere.
All right.
Okay, I'm officially intrigued. Tell me more.
All right, so the catch is this. Some Turing machines, given certain inputs, they might just run forever without stopping.
So it's like a computer program that's just stuck in a loop.
Yeah,
and never actually solves the problem.
exactly.
That seems frustrating.
It can be very frustrating, and this leads us to something called the halting problem.
The halting problem.
Yeah,
That-
so the question is, given a Turing machine and a specific input,
Can we always figure out if it will eventually halt or if it'll just keep running forever?
it seems like we should be able to, right?
You would think so, right?
Yeah.
Like there should be some kind of program.
Right, a halt detector that
Exactly.
can just analyze other programs and tell you.
Right, exactly.
Oh.
Well, what Alan Turing actually proved is that this halting problem is undecidable,
Meaning?
meaning there's no universal algorithm, no matter how clever, that can solve this problem for all Turing machines and all possible inputs.
So there are some computations that we just can't predict will ever end, even in theory.
That's right.
Wow, that's a pretty big deal.
It is a very big deal. And for our philosopher listener,
Yeah,
I think it raises some really deep questions about the limits of what we can know
for sure.
and predict,
Yeah.
even in a purely mathematical sense.
Okay, so we've gone from Hilbert's dream of this, like, universal math solver
Right.
to the realization that even figuring out if a program will stop is impossible sometimes.
Yeah.
Where do we even go from here? So now that we sort of touched on the limits of what's computable, let's explore what we can compute. And dive into this fascinating class of functions called primitive recursive functions.
Primitive recursive functions. That sounds...
It's a mouthful.
It does. It almost sounds like a contradiction. How can something be both primitive and recursive at the same time?
Yeah, it is a bit of a head scratcher, but it really highlights how even with very simple building blocks, we can create these incredibly powerful functions.
Okay.
Think of it like starting with a basic set of Legos, right?
Okay. I like that analogy.
You have your basic actions like, adding one to a number or just identifying a specific number.
Okay. So those are our mathematical Lego bricks.
Exactly.
So we do with them.
Well, we combine them using two main ways. The first is composition,
Okay.
which is basically plugging one function into another, like building a tower with your Legos.
Okay.
And then there's primitive recursion. And this lets us define a function in terms of itself, but using a smaller input.
So it's like creating a chain of Legos where each link is built using the previous one, but it's, modified a bit.
Yeah, exactly. That's a great way to put it.
So we're essentially building up these more and more elaborate structures just by combining and repeating these basic operations.
Yeah, it's quite elegant, actually.
It does sound elegant.
And the surprising thing is, even with this seemingly limited toolkit,
Right.
we can create a huge variety of functions. Think addition, multiplication, exponentiation,
Okay.
all from these basic building blocks.
So I'm starting to see the magic of recursion here, but you said earlier that these functions can grow incredibly fast.
Oh, yeah.
Got an example that would really blow our philosopher listeners' mind.
Oh, absolutely. Imagine a hyper-exponential function.
Okay.
So picture this. We start with the number 2, we raise it to the power of 2, then raise that result to the power of 2 again, and we just keep going, building this tower of exponents.
Wow.
The height of that tower is determined by the input to the function. And even with a small input, like 4, the output is a number so vast,
Gotcha.
it would take more zeros to write it down than there are particles in the observable universe.
That's just mind-boggling. It makes you realize just how powerful these simple recursive operations can be.
They are very powerful.
But are you telling me that even these like hyper-exponential giants, they don't cover all computable functions? There's still more.
You're right. There are computable functions that even these rapidly growing monsters can't quite capture.
Okay.
To get there, we need a new tool, a kind of wildcard operator.
Okay.
We call it the unbounded minimization operator, or MU for short.
Moo sounds mysterious.
It is. It introduces the idea of an unbounded search.
Okay.
Imagine searching for a needle in an infinite haystack.
I've heard that analogy before.
Yeah, right.
Same.
So primitive recursion is like systematically combing through the haystack in a predictable way.
Right.
But MU lets us kind of jump around, explore different parts of the haystack without any predefined limit until we find that needle.
So it's like we're adding a bit of chaos to our otherwise like orderly world of recursion.
Yeah, I like that.
Okay.
We're no longer bound by these, strict, predictable steps.
Right.
And by adding this MU to our toolkit,
Okay.
we expand from these primitive recursive functions to the realm of general recursive functions.
Okay.
And here's the really interesting part. These general recursive functions,
Yeah.
They're exactly equivalent to what those Turing machines we talked about can compute.
Wow, that's a really amazing connection.
Yeah.
We've gone from these simple building blocks
Right.
to like the full power of Turing machines, which you said can theoretically compute anything.
In principle, yeah.
But this brings up a question.
Yep.
We've talked about what's computable in principle, but isn't there a difference between what's computable and what's actually doable,
Yeah.
given like the limits of time and resources in the real world?
Absolutely. We don't have an eternity to wait for an answer.
Right. Exactly.
And this is where we get into the world of computational complexity.
Okay.
It's not just about whether a problem can be solved,
Uh-huh.
but how efficiently it can be solved.
Right, because a solution that takes 1 billion years to compute is not really that useful.
Exactly. So in computational complexity,
Okay.
we classify problems based on how the resources needed to solve them grow as the size of the input increases.
Okay, so bigger input,
Yeah.
more complex problem,
Uh-huh.
more resources needed.
Exactly.
Makes sense.
So a helpful concept here is something called the complexity class P,
Okay.
which stands for problems solvable in polynomial time.
Polynomial time.
Yeah, so this means that the time it takes to solve a problem in P, it grows at a rate that can be described by a polynomial function
Oh,
of
sure.
the input size.
To put it simply, these are problems we can solve in a reasonable amount of time.
That's the general idea, yeah.
Okay.
Now, things get a little more interesting when we introduce NP. Yeah, which stands for non-deterministic polynomial time.
Non-deterministic. It sounds like we're like introducing some randomness or uncertainty into the mix now.
Yeah, it's a good way to think about it.
Okay.
So NP problems are those where a potential solution can be verified quickly
Mm.
in polynomial time,
Okay.
but we don't necessarily have an efficient way to find those solutions in the first place.
Okay, so it's like being handed a completed jigsaw puzzle
Yeah,
and being able to quickly check that all the pieces fit,
exactly.
but not necessarily having a good way to like put the puzzle together from scratch.
That's a perfect analogy.
Okay.
So now imagine this giant, incredibly complex jigsaw puzzle
Okay.
representing a mathematical problem.
Got it.
That's what we're dealing with in NP. And here's the million-dollar question.
Okay, hit me with it.
Does P equal NP?
Ooh, okay.
In other words, if we can easily verify a solution to a problem,
Yeah.
does that automatically mean there's also an easy way to find that solution?
That's a big question.
It is a huge question. And if P does equal NP, yeah,
It would mean that finding answers is fundamentally no harder than checking them.
wow, that would have some huge implications for our understanding of problem solving in general.
Absolutely, for problem solving.
Knowledge.
Yeah,
And even the nature of truth itself.
exactly. And those are the kinds of questions that have been baffling mathematicians and computer scientists
Right.
for decades now. And I think our philosopher listener would find that particularly intriguing.
It's really amazing how we've gone from Hilbert's dream of this universal truth checker to the power and the limits of these Turing machines, and then this whole mind-boggling world of computational complexity.
It has been quite a journey.
Yeah, it makes you think about, the implications for how we understand the universe, right? What if reality itself is, at its core, some kind of, grand computation?
Yeah, I mean, that's a question that physicists have been wrestling with for a while now.
Right, exactly. And if that's true, then these questions about computability and complexity, they
Uh-huh.
take on a whole new meaning.
Yeah, they really do.
Think about, like, the undecidability of the halting problem.
Right, exactly.
Just to remind me and our listeners, what was the halting problem again?
So it's the problem of determining whether a given program, any program will eventually stop running or just loop forever.
Right. And Turing proved that there's no general algorithm that can solve that problem for all programs.
Exactly. No matter how clever you are, you can't create an algorithm that will always tell you if a program will halt or not.
Wow. And so if the universe itself is like this giant computation,
Yeah.
then the halting problem could mean there are just like inherent limits on what we can know or predict about the future, right?
It's a pretty mind-blowing possibility, isn't it?
It is. Are you saying there might be events or outcomes that are just impossible to foresee, even with like unlimited computational power? Because trying to predict them would just lead to this like endless calculation.
It's possible, and it suggests a certain humility when we're trying to understand the universe, right? We might be able to model and understand a lot,
Mm-hmm.
but some things might always remain beyond our reach.
It's almost like the universe is playing a game with us, like
Yeah.
revealing some of its secrets, but keeping others locked away forever.
I like that. A beautiful mystery.
It is. It is a mystery.
And it's that sense of wonder, I think,
Yeah.
that keeps us exploring, keeps us asking questions, keeps us pushing the boundaries of knowledge.
Well, on that note, I want to thank you for taking us on this incredible deep dive into computability and complexity.
My pleasure.
I think it's safe to say our philosopher listener has a lot to think about.
I think so.
And to all our listeners out there, thank you for joining us.
Yes, thank you.
We hope this deep dive has sparked your curiosity and maybe inspired you to explore these topics even further. Until next time, keep questioning, keep learning, and keep exploring the universe's endless mysteries.